Welcome back to the lecture number 16 of this course. So, in the last lecture we are discussing about the solvation dynamics, right. So, when a molecule is being excited from the ground state to the excited state and there is a change in the dipole moment, let us consider that dipole moment has been increased during the excitation. That means, mu g is less than mu e. In that case, the solvent molecule will solvate the excited state dipole moment of the species. In the ground state, the solvation structure by the solvent molecules was different than in the excited state. In that case, right, because the solvent reorientation is not instantaneous, then I would get a different solvated state as a function of time. That is what I was discussing last day. Suppose this is my solvent dipole, suppose this is my solute over here, and this is the random orientation of the solvent molecule. These are the solvent molecules. Okay. So, upon excitation, right, this is my excitation H nu absorption of this molecule. So, I am going to create a dipole like that way. So, just after the excitation, these solvent molecules, right, these are the solvent molecules, they will have the similar orientation that of in the ground state, but as time goes, here is my time axis, here as time goes. So, these solvent molecule will reorient themselves, and at each step in between these, right, that emission spectra will come. So, when the solvation structure is such that the energy of this excited state dipole is over here, then the emission will come from here. When the energy is like this, then the emission will come from this state. When energy is like that, then emission is like this, and when it is fully solvated at this state, so then the energy will come from this state, right. So, when you measure this emission spectra of this particular solute molecule, right, that means you are monitoring the excited state of the species. So, you will get the contribution from this state will be more, but the contribution of all these state will be there. That means, it is the time integration of all these different emission spectra over time, right. So, if you have some way to get the emission spectra of the solute molecule as a function of time, then at very early time, right, what you will get? You will get the emission spectra which is originating from this particular state, right, and at the later time you will get the emission spectra which is originating from this particular state. Obviously, this state emission spectra will be more blue shifted for this will be the blue shifted, and this will be the red shifted. That means, this emission spectra will be of higher energy and this emission spectra will be of lower energy. Just to show you this, I have one small video over here. So, let us say this is your solute molecule, and after the photoexcitation, that dipole has been created instantaneously. Now, if you see that orientation of the solvent molecules are random, right, but when the dipole has been created, in this case as you can see over here. So, as the dipole will created, these solvent molecules will reorient themselves to stabilize the species, right. Now, if we just look at this energy of this excited state, that during this solvation the energy will keep on decrease and decrease and decrease, and at this finally it will be solvated fully, right. So, the emission spectra will start from here and then it will end over here. That means, I will get a time dependent emission spectra. That means, if this is known as time dependent fluorescence Stokes shift. So, Stokes shift is being changed, right, because of the solvation, and if I now plot this emission spectra as a function of time, what you will see that at time t1, right, which is the lesser time, the smaller time, right, just after the excitation, this emission is like this way. As time goes, the emission will shift to the longer wavelength. Now, as I said, the steady state emission spectra of this molecule is nothing but the time integrated spectra of all these different times, right. So, the steady state will be somewhere here where the contribution of this one will be very small because it exists only for a very short time, right, but the contribution of this guy will be large because this is my equilibrium structure, equilibrium solvation structure of this solute dipole. On the other hand, if you see that at time t equal to 0, right, this species has not formed because it took some time to form this stabilized structure. So, at time t equal to 0, this species has not formed. So, if I now take the intensity versus time at different wavelengths, then the intensity versus time plot of different wavelengths should behave differently. What I wanted to say is that let us take this particular wavelength lambda 3 over here. In case of lambda 3, so if you start measuring the fluorescence intensity after the photoexcitation. So, if you start measuring the fluorescence intensity after photoexcitation at time t equal to 0, right, there is no fluorescence intensity, as you can see over here, the value is 0, right. But as time goes, that fluorescence intensity will increase. So, if I now draw some other emission spectra here, so let us say time t2 prime, that may looks something like this, right. So, here at time t2 prime we got small emission intensity over here. As time goes, this spectra will shift like this way, and this emission intensity will increase from here to here, from here to here, from here to here, and so on and so forth. That means, if I plot the emission intensity of lambda 3, right, as a function of time, I must be able to see first increase in the fluorescence intensity, then obviously the fluorescence intensity will decrease because of the lifetime of this molecule. On the other hand, if you see this lambda 1 wavelength, right, lambda 1 wavelength, then just after the excitation, the emission intensity is maxima. So, it will start from this maximum value, right, instantaneously, and then it will decay as per its own lifetime, that means 1 over k r plus k n r, as well as this intensity will decrease because of the shift in the emission spectra, right. So, if I now plot, just see here that I have plotted it. So, this is in case of lambda 3, you see that emission spectra was less over here and the emission spectra increased like this way, and then it will decrease, right. So, that decrease is just because of its own lifetime, fluorescence lifetime. On the other hand, if you see this lambda 1, you see from the beginning it started decreasing, like this way, right. So, from the measured lifetime means these graphs, from measured these graphs is nothing but fluorescence intensity versus time for different emission wavelength. I can get back this from here, I can measure this guy, and I can convert this to here, and this process is known as the formation or construction of time resolved emission spectra. Let us see how we can do that. So, as I said here, the construction of time resolved emission spectra, and it can be done by recording the fluorescence decay at different wavelengths, right. And this is my fluorescence decay. Lambda I is a function of lambda t, because it is also function of lambda, because at different wavelength, right, emission intensity is different, as I showed here. This is for lambda 1, this is for lambda 3, that means it depends on the wavelength, right. And also it depends on the time, that is because of its natural lifetime, 1 over k r plus k n r, right. So, and here we can say that this I, which is a function of lambda and t, can be written as a lambda and b t. So, a quantity which depends only on the lambda, this is my that Stokes shift part, and this is my natural lifetime part, right, which is a lambda into b t. Okay. So, now if and earlier what I showed you that this Bt is exponential in nature, right. So, if I integrate this Bt over 0 to infinity, that means the full time region, then what I will going to see is integration 0 to infinity a e to the power minus t by tau, where a is its amplitude. It may be 1, it may be 100, it may be 1000 depending on the initial fluorescence intensity, right. So, it is a and e to the power minus t by tau, this t is my variable this time and this tau is the lifetime of that species and dt. So, if I do this integration, what I will going to get is a minus tau e to the power minus t by tau, that limit is 0 and infinity, which will going to give me a tau. Now, if it is not a single exponential function, here is my single exponential decay. So, I will get this one. If it is a multi exponential decay, so for multi exponential decay, this will going to be sum over I a I tau I. In this case, the decay function is sum over I a I e to the power minus t by tau I. This is my fluorescence decay, right. It means a1 e to the power minus t by tau 1 plus a2 e to the power minus t by tau 2 and so on, depending on the value of I. Okay. So, now let me write here the steady state intensity is defined, let me define as ISS. Obviously, it is a function of lambda, right. So, that is nothing but integration 0 to infinity I lambda t dt, right. And in this case, I have separated this. So, one is a function of lambda and integration 0 to infinity bt dt, and I already got the value of bt dt, integration 0 to infinity bt dt. So, this is nothing but a lambda, a is a function of lambda and sum over I a I tau I, right. So, if I want to calculate this a lambda is I can write it as I steady state lambda divided by sum over I a I tau I from this relation, right. So, from here what I can write, I, which is a function of lambda t, is equal to I steady state for this particular, I am talking about that for this particular lambda, right. For different lambda, I have to do that same thing again and again. So, this is equal to sum over I a I tau I into sum over I a I e to the power minus t by tau I, right. So, I got this equation. So, in this equation you see that for a particular lambda, for a particular value of wavelength, what I got that how the intensity will vary with time, right. And so, if you have different wavelengths, right. So, for a particular time you can plot the intensity at different lambda, for a particular time the intensity at different lambda, that means different emission wavelength. So, that can be calculated from here. This is nothing but this lifetime of the molecule, and here is my steady state intensity over here, and here is again that lifetime component a I and tau I. So, if I just show you this plot over here, as you can see here at shorter time, right. So, this is my spectra, this is plotted in nu bar. So, So, in this case this is my shorter time spectra. So, here you see that these intensities are like this way, intensities are like this way for different lambda or different nu bar. These are the corresponding nu bar, these are the corresponding nu bar, right, as shown here. Now, if I change the time from this time to this time, let us say this is tau t prime, let us say this is t double prime, and I recalculate this thing, you see the position, the intensity of all these lambdas are now different. So, it was like here, now it become here for different value of t. It was for t prime, but this is now for t double prime, but at the same wavelength or same wave number, right. So, if I plot this time dependence of this emission spectra, then I will get an idea that how the system is getting stabilized or how the whole system is getting solvated by the solvation. Nevertheless, what we need to get this I lambda t is these quantities, right, this one, right, these quantities. This is okay, no? Because we already know how to measure the emission spectra in the steady state, that is time integrated emission spectra. But I although talked about the lifetime, but I have not talked about that how we are going to measure this fluorescence lifetime. So, measurement of fluorescence lifetime is important. So, let us see that how we are going to measure this fluorescence lifetime. As I said earlier that fluorescence lifetime of a sample tau, it means that the average time the molecule spend in the excited state. Let us take this molecule, right, this molecule I have taken in this box, and these molecules are excited with an instantaneous flash, right. That means the time taken for excitation I have assumed that is infinitely small delta function. So, immediately all the molecules are taken into the excited state. Ideal situation, real situation I will come later. So, ideal situation, all the molecules are now in the excited state. So, in this case you can see over here the green color represent that the molecules are in the excited state. So, now if you start looking at that what is the fate of this molecule, the molecule will come back to the ground state, but it is not like that, that all this molecule will come back from the excited state to the ground state all of a sudden. All the molecule will come back at a particular time delay between the excitation, right. What happens is that some molecule will come back from the excited state to the ground state at the early time, some will come at the later time. As I have tried to show you by this animation, as you can see here that this molecule was in the excited state, now it is become in the ground state. So, this molecule is in the excited state, now it is in the ground state, right. So, that green means excited state, white means ground state. So, it is a random process, It means, let me run it again. So, here when all the molecule was in the excited state, the emission intensity was maximum, right. As time goes, the emission intensity is decreasing, right, as the molecules is coming back from the excited state to the ground state. And I already have discussed when this value is like 37%, then we say that this time is my fluorescence lifetime of the sample. Now, question is that how we are going to measure it, right, how we are going to measure this tau, or how we are going to measure such kind of decay, or how we are going to measure this intensity versus time. If this time is in the time window of hours, then no problem. I can simply take this molecule in my fluorimeter, I measure the intensity now, I measure the intensity after 2 seconds, I measure the intensity after 5 seconds, and so on, and keep on measuring for an hour or so, and I will get this plot. But the problem is that, as I said earlier, the lifetime of these molecules are in the order of nanosecond. That means, you need to measure all this time in picosecond time resolution, right. 10 picosecond, 100 picosecond time resolution. So, that is what you see here. I have written the time picosecond over here, right, is the picosecond over here. That means, you must have a stopwatch, right, or a machine which can measure the time in the picosecond time region, right, at least in the picosecond time region. So, picosecond is 10 to the power minus 12 second, as you know, and that kind first stopwatch obviously is not available easily in the market. So, we need a special treatment to get such kind of decay. Basically, the idea is just after the excitation, all the molecules are in the excited state considering the 100% excitation, which is not true again, but for this basic course let me consider that on excitation all the molecules are now in the excited state, and if you measure the fluorescence intensity as a function of time, then the fluorescence intensity should decrease, right, gradually, and if you plot that intensity versus time, you will get exponential type of curve. If it is single exponential, it is a bi-exponential, then the curve will be little bit distorted and so on and so forth. So, ultimately you will get the intensity versus time plot, and from there you will be able to calculate what is the value of the lifetime tau, right. So, now let us discuss how we are going to measure. As I said that lifetime can be measured in two ways. One is the frequency domain method, another is the time domain method, but in this course I will discuss only the time domain method. So, in the time domain method, as I said that we will going to excite the molecule with instantaneous pulse. That is what I have shown here with this dotted line over here. So, this time, right, this time is very small time, very small compared to this decay, right. That means that when you are exciting this molecule, all the molecule will go to the excited state all of a sudden, right. There is no time required to take this all the molecule from ground state to the excited state. That is what I consider here. So, this is known as the excitation pulse, right. So, this excitation pulse is very short, in time. Okay. Let us consider that this is a delta pulse, that means the width is 0, delta pulse. Now, after excitation, this emission intensity, let us consider 1, it may be 1000, maybe 1 lakh, maybe 1 crore, but I can always normalize it to 1. So, let us say that this emission intensity is 1, right, and then I will monitor how the emission intensity is decreasing as mentioned, and from here I will get whenever that remaining part is on 37% or so, then I will say that this time is my lifetime, and I will get all these intensity values as a function of time, right. So, I need to measure it. The question is how I am going to do that. In time domain there are 3 different way to measure it. The first one, let me write, is time correlated single photon counting method. In short, it is known as TCSPC. Second one is streak camera, also this is very popular, and the third one is fluorescence upconversion method. So, this is also very popular. All these methods are popular. Each method had its own advantage and own disadvantage. First, let me tell you this about this time correlated single photon counting, and I will not going to discuss this streak camera because it is little complicated and I do not want to discuss this in this basic course, and then I will discuss about this fluorescence upconversion, right. Okay. So, let me draw the basic setup of this time correlated single photon counting. So, here what you need a laser. Why I need laser? Because I want to create a short pulse. The laser has unique property that it can create ultra short light pulse. I said that in my previous discussion over here, I said that very short in time, that kind of excitation pulse I need. How short pulse you can create, right? For, let us say, for a light bulb, if you turn it on and off very quickly, it could be 1/10 second. So, light is on only for 1/10 second, that means 10 to the power minus 1 second. But I need 10 to the power minus 12 second, I need 10 to the power minus 15 second. How I am going to get that? You cannot make a electrical device by which you can turn on and turn off so fast, right. So, I need some unique device which can generate such kind of short light pulse, and laser is one of is the device which can generate that short light pulse. I will discuss very briefly about how we are going to get this ultra short light pulse by laser, but now let me consider to draw that basic setup of this TC-SPC system. So, this is my TC-SPC, and here I have this laser, and just after the laser I have something over here, then I have my sample is placing over here. So, when the laser light will come, it will excite the molecule, and I have again something over here. I will discuss what are these things later, right, because it is not yet the time to discuss these things, and then emission will come from this side. I will going to have here my monochromator, to choose the emission wavelength. Then I have a device which is called TAC, time to amplitude converter, which is connected to the computer. This device is very basic TC-SPC setup for our discussion, and today the time is up. So, I will continue the discussion on the next day. Thank you for your kind attention.